who have consistently supporting our webinar series. Actually, your enthusiasm has kept our knowledge sharing platform vibrant and impactful. I encourage all of you to actively participate, ask questions, and make the most of this opportunity. A gentle reminder, e-certificates will be provided to all participants, and the IA member with the highest participation across sessions will be honored during forthcoming Engineers Day 2025 celebrations. Let us celebrate this National Technology Day with a renewed commitment to innovation, sustainability, and collaboration. Once again, I extend a warm welcome to each one of you. Let us together make this evening enriching and inspiring. It's my privilege and proud to introduce today's speaker, Dr. G. Fatima ma'am. Dr. G. Fatima ma'am has done her BE at Tyagarajar College of Engineering, Madurai, ME at NIT Trichy, and PhD from Anna University, Chennai in the year 2012 in the field of computer science and engineering. Ma'am has started her teaching career as lecturer in 1994 and elevated as assistant professor, associate professor, and professor. Ma'am has more than 25 years of teaching experience and more than 17 years of administrative experience. Ma'am is the institution's SPOC for the Smart India Hackathon, and numerous teams have competed in the grand finale under ma'am's guidance. Ma'am also organized several number of national and international symposium, workshops, seminars, and also student project competitions for the benefit of budding engineers. Ma'am has organized more number of FDPs for the benefit of faculty members and also industry persons. Ma'am also published 33 papers in international journals and also presented more than 30 papers in various international and national conferences. Ma'am has filed and published 4 patents, out of which one patent has got granted. Ma'am also authored 11 books and book chapters. Ma'am received a grant for the research projects from UGC, AICT, IEI, and also TNSC, ST. Ma'am is a life member in ISTE and IEI. Ma'am received the Best Project Award from IEI. Ma'am received International Educator of the Year 2022 award from I2R, Senior Educator and Scholar Award from NFED, Best Administrated Award from Abdul Kalam Educational Trust. Ma'am also received a Faculty Excellence Award from Infosys. Also, ma'am's area of interest includes mobile ad hoc network, cryptography, data mining, and image processing. Ma'am is a recognized supervisor of Anna University, Chennai. 2 scholars have been awarded doctoral degree under ma'am's guideship. 8 scholars are now pursuing under ma'am's guidance. Ma'am is also doctoral committee member of scholars at VTU and VIT universities. Ma'am is an enthusiastic educator with a genuine passion for teaching and a strong commitment to students' growth. Also, ma'am is eager to foster a dynamic learning environment that engages and empowers students. To add on, ma'am embraces challenges as opportunities for growth, continuously seeking innovative ways to enhance the learning experiences. Also, currently, ma'am serving as professor and head of the department of CSE department of Adiyaman College of Engineering, Hosur, Tamil Nadu, India. Before Hosur Center, also ma'am is our proud committee member of Salem Local Center. With this again brief introduction, I invite ma'am for the lecture. Ma'am, the stage is now yours. Ma'am, I think your mic is mute, ma'am.
Okay, okay. So thank you, sir, for the wonderful introduction. And shall I start the presentation?
Yes, ma'am.
Okay. Hope my presentation is visible.
Yes, ma'am, visible, ma'am.
Okay. Am I audible now? Right?
Yes, ma'am, audible, ma'am.
Okay, okay. So let me start the presentation. So before getting into my presentation, I'd like to take this opportunity to thank the organizers for inviting me to share my knowledge with you all during this National Technologies Day celebration of IEI, Salem Local Center. Actually, it is truly a pleasure to join you for this session, and I'm very much delighted to speak on the topic of quantum computing, redefining the limits. Today we will explore how quantum computing is not just an evolution of classical computing, but a revolution that defines the very foundation of how we process the information. Actually, I'm not an expert in quantum computing. Still, I'm excited to share my knowledge on this fascinating and transformating topic with you all, starting from the basics of quantum computing, its application challenges, and end with the future of quantum computing. Let me know how many of these participants are aware of this quantum computing or new to quantum computing. Any inputs can I get from the participants? I hope I'm audible.
Yes, ma'am.
Okay,
Ma'am,
okay,
only I know the basic things, ma'am. What is second bit? What is qubit?
okay,
Only those things, ma'am.
okay, okay. And so this session will be only a comprehensive overview of this because with a limited time, I can give you a comprehensive overview of this quantum computing. And as you may be aware that the United Nations has named this 2025 year as the International Year of Quantum Science and Technology. This is for honoring the 100 years of quantum science. The goal is to get the more people interested in and aware of this quantum science, focusing on how much it affects today's technology and society. Because the quantum technology is driving big changes in computing and communication. And as these systems becomes easier to use and expand, they are ready to change the industries and push the technology to new levels. So this shift has already happening today, and it is going to reshape the world around us tomorrow. So this year, 2025, is really a breakthrough year for quantum computing, and it is going to be a big game changer. The leading companies like Microsoft, Google, IBM are racing to build stable and scalable quantum systems, and they are bringing new ideas that could change the future of computing. So on seeing these fast-paced global strides, it is clear that we are standing at the edge of a technological breakthrough. So before we are dwelling into this quantum computing, let me take a moment to recollect the Moore's law. because we should understand why we are again focusing towards the quantum computing. So I hope everyone are aware of it. This Moore's law. This principle is the one which has guided the progress of classical computers for decades. So Moore's law, proposed by Gordon Moore in 1965, states that the number of transistors on a microchip doubles approximately every 2 years, and while the cost per transistor decreases. And this has driven the exponential growth in computing power, leading to a remarkable technological advancements, and which is what we are experiencing today. And this has worked well for a long time, but now we have reached the physical limits of miniaturizing the transistors. Thus, the exponential growth has begun to slow down. The transistors have become so small, almost the size of the atoms, because of which it has become very difficult to make the computers faster using the classical computing architectures. And it is also a big challenge too. So this is where the quantum computer comes into picture. So you can, here I've just given you a glimpse of how the number of transistors has increased the scale from the year 1972 to 2020. And so unlike the classical computers, which rely on the binary transistors, quantum computers leverage the principle of quantum mechanics to perform calculations. Instead of relying on transistors like regular computer, quantum computers use the principle of quantum physics such as superposition and entanglement to process the information that is in a completely different way, that is new way. So this makes them to solve the problem that are practically impossible for classical computers. So here I have given you the definition of a quantum computer. It is a machine that performs a calculation based on the laws of quantum mechanics, which is the behavior of particles at the subatomic level. So this quantum computing is not just about making computer faster. It's all about solving problems which regular computers will take a long time to handle, like cracking the advanced codes or optimizing the huge systems or simulating the molecules for new medicines. So actually, it is not just extending the Moore's law, it represents a paradigm shift. What about the visibility of the picture? Okay, so now I can see that you'll be able to see, I think. Now, if you see how the quantum computer looks like, you can see that it is like has a refrigerator-like structure, and it operates in extremely cold temperature, often close to absolute zero, to maintain the delicate quantum states. The main components are typically housed inside a cryostat, which is a cylindrical blocks or cooling system resembling a refrigerator or a large chandelier, and which has been shown or marked here as A and D. This cylinders or cryostat where the quantum processor and the cooling system is placed. Inside the cryostat, you can see a complex structure with golden shiny wires and plates hanging down, which is called as quantum chandelier. So the actual quantum processor, where the qubits are located, is quite small. It has also been shown here, and which is typically a chip-like structure, which is at the bottom of the chandelier. And these qubits are often made from superconducting circuits or trapped ions, depending on the technology. So hundreds of wires and cables connect the quantum chip to control and measurement systems. Shielding is used to protect the qubits from noise and the interference. That's how these quantum computers are looking very big. And suppose systems of what is inside the cylinder, like power supplies and cooling gas, control box. This is what it has been marked as B and C. So let me give an example for an understanding of the working of traditional and quantum computers. Imagine that you are standing in the center of a complicated maze. Now, if you want to find the solution that is find a path to reach or come out of this maze, what the traditional computer would have done is it will brute force the problem and try every possible combination of the paths to find the exit. And this kind of computer would use the bits to explore new paths and remember which ones are the dead ones where you will not be able to go out. But comparatively, if you see the quantum computer, it derives a bird's eye view of the maze. So it tests the multiple paths simultaneously and it finds the correct solution. But however, the qubits do not test the multiple paths at once. Instead, the quantum computers measure the probability amplitudes of qubits to determine the correct solution. So this has become possible because of the property of qubit called superposition. So I'll be discussing about the superposition in the subsequent slide. Now let us understand this qubits. Is it okay? Again, I feel that this is quite disturbing. Is it okay? Because is it okay? My slides, is it okay? Or it is hiding the content, or the bars hiding the content? Is it so?
No, it is okay.
Okay. Okay, now let us understand the qubits. So in traditional or classical computing, a single bit can be thought of as a piece of binary information, which is denoted as either 0 or 1. And these bits are represented either as an electrical voltage or the current pulse. While the classical bits can exist in either 0 or 1 position, whereas if you consider the qubits, it can occupy a third state known as the superposition. Superposition is the one which represents 0 and again the basic state is 0, 1, and the superposition is nothing but all the positions taken at once in between 0 and 1, and that is considered to be the third position, a third state called as the superposition state. And by the qubits encode these three separate positions, they are still used to convey information only through a binary systems. So in such systems, the bit can refer to either the material or the process which is used to represent 0 or 1, and the other one state is called as nothing but the measurement of that bit. And we can label these states as Ket 0. You can see the representation. This is called as the Ket 0 and Ket 1, and this called as, again, this notation is called as the Dirac notation. Here, let us discuss about the features of qubits. First, coming to this superposition, unlike classical bits, as I was telling you, unlike the classical bits, which can be either 0 or 1, this qubits can exist in the state known as the superposition state. Whether they can be either 0 or 1 or both simultaneously. And this is due to the principle of quantum mechanics, which allow the particles to exist in the multiple state at once. For example, imagine a coin spinning in the air. It is not just the head or tail, but both simultaneously. So this ability to hold multiple states allow the quantum computers to perform the many calculations at once. So for better understanding, I have given you here a picture which will again recollect the concept of the Schrodinger's cat experiment. So here you can see that assume that you have a cat placed inside the sealed box along with a radioactive atom and Geiger counter to detect the decay and a vial poison triggered by that deduction. If the atom decays, the detector releases the poison and the cat dies. If the atom does not decay, the cat stays alive. That is the scenario. And now here is a twist. In quantum mechanism, until we observe the system, the atom exists in superposition. Thus, it is both decayed and not decayed at the same time. Since the cat life depends on the atom, it also enters the superposition state. Collapses into a, again, when if a cat is both, that is, both alive and dead at the same time, and when if you open and observe the box, then this superposition state collapses into a definite state. So here the cat is alive or dead, but not both anymore. And this is how we have to understand the concept of superposition. I hope it is clear. So this superposition is what gives the quantum computers their incredible potential. So when a qubit is in a superposition state, it can perform multiple calculations simultaneously. So this is what it is the biggest change or compared to that of the classical computers. So next we will move on to the next property called the entangled property. Here, when two qubits are entangled, there exists a special connection between them. It means that the state of one qubit is linked to the state of another, no matter how far apart they are. So changing the state of one entangled qubit will instantly affect its partner, and this property enables powerful correlations and faster computations in quantum systems. For example, consider the two particles are closely linked and one particle is at my home, another one is at your home. So whenever the behavior of one particle which is at my home changes, it will immediately affect the state of the other particle which is at your home or vice versa. The next is about the quantum interference. This is the other property of quantum, again, a qubit. And here, the quantum computers use the interference to manipulate the probabilities of qubit states by amplifying the probabilities of correct solutions and cancelling out the incorrect ones. And the quantum computers the quantum computers can solve certain problems more efficiently. That's what I was telling you about the maze problem. And this will be used in amplifying the correct solutions and cancelling out the incorrect ones. So these characteristics of the quantum mechanics makes the quantum computing very interesting to study and implement. So next we will move on to the representation of the qubits. And this is it is called as the Dirac notation, and this is pronounced as Ket-Psi. Yeah, this one is called as Ket-Psi. Okay, again, if you want to break down, it is nothing but a vertical bar is called as the Ket, and the Greek letter is called as Psi, and this angle bracket which is not separately pronounced, so together you call it as the Ket-Psi notation. Okay, and they again and this and here if you see that the quantum state that is Ket-Psi is represented as alpha Ket0 plus beta Ket1, and this Ket0 and Ket1 are the basic state, and this alpha and beta is nothing but the probability amplitude of these states respectively. And this entire equation, which represents the superposition state. Okay. And you can see that to here, and this is nothing but the Ket0. Again, it is represented in the vector representation as 1, 0, or Ket1 is represented as 0, 1. And here you can see that alpha square and beta square are the probabilities of measuring the qubits as 0 or 1. And this alpha and beta are complex numbers, whereas if you have this alpha square plus beta square, it is equated to 1. It is equals 1s. So here I have given you the vector representation, and here if you see that the basic states Ket0 and Ket1 are represented as the column vector 1, 0, 0, 1, or you can even represent as the row vector like this. Okay, And any arbitrary state can be represented as ket psi, that is alpha or beta, or alpha ket 0 plus beta ket 1. And these are the sum of the valid quantum states vectors. And and here ket plus, that is, and ket minus are called the Hadamard basis, and these are orthogonal to each other. So here is the comparison given between the classical bit and the quantum bit. And you can see here this classical bits, how again the classical bits differs from the quantum bits. That is, it can be again without the three states. Again, whereas classical bits, if you see that it is measured completely, whereas quantum bits can be measured partially with a given probability. And classical bits is not changed by the measurement, whereas the quantum bits are changed by the measurements. And if you see that the classical bits cannot can be copied and erased, whereas the quantum bits cannot be copied and erased. So next we will move on to the physical implementation of qubits. Qubits are created using the various physical systems such as superconducting circuits or trapped ions or photons or neutral atoms. So let us see about this again, how this can be used to create the qubits. Superconducting circuits are the one of the leading physical implementation of qubits in quantum computing, and they rely on the superconducting materials, typically niobium or aluminium, and which is cooled to extremely low temperatures, actually near to absolute zero, to eliminate the electrical resistance and allow for coherent quantum states. And next, coming to the trapped ions. And trapped ion qubits are another leading approach in quantum computing, and they use individual ions or charged atoms suspended in a vacuum and manipulated using the electromagnetic fields to perform the quantum operations. And these trapped ion qubits are noteworthy for long coherence times as well as high fidelity measurements. Coming to the quantum dots, they are the tiny semiconductor structures that can trap individual electrons and use their spin states as qubits in quantum computing. And these quantum dot qubits can be manipulated using the magnetic fields and are particularly interesting for researchers for their potential scalability and compatibility with the existing semiconductor technology. The next is the photons. The photon qubits are a game changer for quantum communication. So unlike the other qubit types, which require extremely cooling or precise electromagnetic control, photon qubits leverage the fundamental properties of light. So by setting and measuring the directional spin states of individual light particles, photon qubits can be used to send quantum information across long distances through optical fiber cables and are currently being used in quantum communication. The next is the neutral atoms. And these qubits are promising approach in quantum computing, offering a scalability and precise control over the using the laser-based techniques. So using laser, these atoms can be charged with the energy into a number of excited states, and any two of which can be used to create a qubit, which is well suited for scaling of operations. So here in this there are these are the some of the types of qubits I have given, and then how it is getting created physically. But if you see that not all the qubits that has been created are same. So let us explore the different qubit types and the companies using it. For example, if you see here, so we have a superconducting qubit used by the companies like IBM, Google, and Rekti. And these qubits are built using the superconducting circuits and are known for their fast gate times, which means that they can perform the operations very quickly. But the downside of this is they require extremely cold temperature, close to absolute zero, and so they need a complex cryogenic systems. Now, but if you consider the trapped ion qubits, they are developed by the companies like IonQ and Honeywell, and these use charged atoms trapped by the lasers or electromagnetic fields. And the key advantage is long coherence time, and they maintain the quantum state for longer, that is, and which is great for computation accuracy. However, they suffer from slower gate operations, so calculations take more time. Then are the photonic qubits used by Xanadu and Psi quantum, and these qubits are made of particles of light or photons. And the benefit is they don't need cooling and they can operate at room temperature. But the challenge is the photon interactions are difficult to control, which makes the building reliable on quantum gate, logic gates are harder. And the next, finally, we have the neutral atoms, which is explored by Q era and Pascal. And they are they use the neutral atoms arranged in space and manipulating using laser arrays. And this approach actually offers the scalability, which is very important for building the large quantum computers. But the thing is, it is relatively new and experimental method, not yet mature enough. So different companies are using different qubits, and each of it have their own strength and weaknesses. Now, next, we will see about the quantum gates, because these are the basic building blocks of the quantum circuits. So much like a classical logic gates, like AND or NOT in digital circuits. However, but unlike classical gates, quantum gates operate on qubits, which can exist in superposition of states and create entanglement. And the other important thing is they are reversible, and each can be represented by a matrix. So let me just show you some of the quantum gates. Here we can see some of the common single qubit quantum gate, like X gate. So actually it is X gate is otherwise called as poly X gate, poly Y gate, and then Hadamard gate called as nothing but the H gate. And there are common two qubit gates like C naught gate. And you have other gate called that is CZ gate, and 3 qubit gate is nothing but the T gate. Okay, so if you come across this X gate, that is the poly X gate, it flips the qubit just like a classical NOT gate. And if a qubit is in state, for example, the qubit is in the state gate 0, it becomes gate 1 and vice versa. Whereas if you consider the poly Y gate, it flips the qubit. But actually what it flips is flips the phase, and that is the plus or minus I. It is like a complex version of the X gate, which I have not shown here. And the other one is the poly Z gate. And here next, and the next one is the Hadamard gate. And this is very important gate actually. Hadamard gate. And this Hadamard gate, it is the one, it is a very plays a very central role in quantum algorithms like Grover's and Shaw's algorithm. And it creates a superposition, and it takes a qubit from a definite state to a mixture of gate 0 and gate 1. You can see here it is represented in the matrix as 1 by root 2 in the matrix, that is 1 by root 2, 1 by root 2, 1 by root 2, then minus 1 by root 2 multiplied by the alpha and beta. So you can see the equation of this Hadamard gate output. Again, the next one is again the Tolley gate. T gate is otherwise called as a Toffoli gate, and it is and this particular gate flips the target qubit only when both the control qubits are 1. And it is used in the quantum error correction and reversible computing. Whereas if you consider this, so that's whatever has been shown here. Again, apart from this, you have 2 qubit gates like a C naught gate and CZ gate. C naught is nothing but the controlled NOT gate, which flips the target bit only if the control bit is 1, and it is it is used for creating the entanglement. And along with the single qubit gates, and it can form the universal gate set. So here again, given you an example of a quantum circuits. This is again, which enables the quantum algorithms. by again this cube quantum logic gates are arranged to build the quantum circuits again so that the quantum algorithms can outperform the classical ones. And here you can see that it is made up of the Hadamard gates with 3 qubits in the input. So I'll not be going in detail about this because you need to have a separate session if you want to understand all these quantum gates. So next we'll move on to the quantum development frameworks. When working with quantum computers, software plays a vital role in designing, simulating, and running quantum algorithms. So here, let us look at 5 popular quantum development frameworks. Each has its own strength. And first, we have like the Qiskit, which is developed by IBM, and it is a full stack framework. And it supports everything from algorithm design to hardware execution. And so all these again it includes powerful simulators, tools for noise modeling, and access to real quantum computers. And next is the CirQ, developed by Google, and it is designed for NISQ devices. And whereas NISQ stands for noisy intermediate scale quantum systems. And it gives you fine-grained control over circuits, which is essential when running algorithms on the imperfect quantum hardware. The next one, Penny Lane, and it is been provided by the Xanadu, which is focusing on the exciting field of quantum machine learning, and it supports differentiable programming, and actually so that it can be used to train the quantum model just like the neural networks. Next one is the Ocean SDK, which has been created by D-Wave, and it is built for different kind of quantum computing called quantum annealing. And this toolkit helps developers solve optimization problems and build hybrid quantum classical applications. And then lastly, you have QTIP, which stands for Quantum Toolbox in Python. And this is the one which is open source library and designed for quantum simulation and control. And it is especially useful for in research and academic environments. So one important thing you have to note here is all these are based on the Python. Okay, and each of these frameworks play a crucial role in pushing the boundaries of what we can do with the quantum technologies. So next, we will move on to the applications of quantum computing. So here I have given you a few applications. Let us explore these applications like finance. In finance, quantum computers can optimize investment portfolios, helping banks like Goldman Sachs and JP Morgan's to make better decisions. And they can rapidly analyze thousands of variables to minimize risk and maximize returns term, so that these perform two complex tasks which is very not impossible, but it's very difficult with the classical computers. And coming to the pharmaceuticals, like companies like Roche, Bayer, and Boehringer are exploring quantum computing to simulate molecular interactions. And because of this, these quantum computers, they perform accurate modeling of drug molecules, and because which can be done dramatically good speed, which can speed up the drug discovery process. So if you come across the classical computers, it may take years together for performing this task, whereas if you make use of the quantum computers, and the time it takes is very less. It may be in terms of again a few minutes. Okay, leading to so this applications will lead to faster and the safer treatments. Now coming to the other applications, it can be used to optimize the complex supply chains, which is the critical need for the companies, and like DHL and Volkswagen are using this. And this is from delivery route optimization to warehouse layout design. And quantum algorithms can be used, which cuts the cost and increases efficiencies, compared to that of the classical systems. The next field is the material science. The quantum computers can simulate the behavior of quantum materials and complex compounds at the atomic level. And this can lead to breakthroughs in battery technologies, semiconductors, carbon capture materials, so which accelerate innovations in clean energy and electronics. And the next is about, again, application is the machine learning. So with the concept of quantum neural networks and variation algorithms, we can train the AI models exponentially faster than what we can do with the classical computers. And by this, it opens the door for the advanced pattern recognition, natural language processing, and optimization task. And the other field is one of the most actually impactful and controversial application is the cryptography. And by making use of the Shor's algorithm, quantum computers can factor large numbers exponentially faster than the classical computers. Actually, this has become a threat for current encryption methods like RSA, which rely on the factoring and considering it to be very hard to factor it. So next we will move on to the I have listed few. Other than that, there are other applications where the quantum computers are being used. Here's I've just shown you a few. Next we will see about the challenges. So what are the biggest hurdles that the researchers and the engineers are working towards? First is the qubit. The qubits are extremely fragile, and they are easily disturbed by their surroundings like temperature, electromagnetic fields, or even cosmic rays. And this has led to the phenomenon called decoherence, where the qubit loses its quantum state before useful computation can be completed. Because if you see in the classical computing, there are only two bits, either 0 or 1, and it is stable. But in quantum computing, a tiny disturbance can collapse the qubit states so that it will spoil the result. And the next challenge is and the error rate. Here, when we apply the operations to the qubits, they are not fully reliable because of these errors. One important thing is they are very harder to detect and correct. So even if you see that the current systems have the error rates around 1 in 1,000. That is, so the quantum algorithm has thousands of steps, and it's very difficult to find out the errors, and it may lead to wrong answers. And the third challenge is the scaling. So to solve the real world problems, the scientists estimate we need millions of qubits. So, for example, if you see that today's quantum computers only have 10 or hundreds of qubits, and many of those are too noisy to use efficiently. So, building reliable and interconnected systems with the millions of high fidelity qubits is a huge engineering task, and which requires the advance in the hardware, cooling system, and quantum interconnects. Then finally, the other challenge we have is the quantum error correction. And all of these is because of the noise and the fragility, and we can't rely on a single physical qubit. So we use the error correction codes that group thousands of physical qubits to create one reliable logical qubit. And this will create a massive resource overhead. So for example, to build a computer with just 1,000 useful qubits, we might need 1 million of physical qubits. So these challenges are why the quantum computers are still in development, and the researchers are making steady progress and solving these problems. So next, let us see about the future of quantum computing. So here I've given you the market growth of quantum computing right from 2020 to 2030. And if you observe the quantum computing rapidly becoming a transformating force in the global global landscape. And according to Gartner, quantum computing market is projected to 1.88 billion in 2025, which is 27.3 increase from 1.48 billion in 2024. So this is just a beginning. By 2029, it is expected that we will reach like a $4.89 billion. So if you try to explore what is driving this explosive growth, there are two main factors. One is the demand for high computational power, which the classical computer are hitting their limits, and the quantum computing promises this exponential speed ups. The other one is the urgency for secure communication. That is, the quantum computers could eventually break the current encryption. So there is a growing need to develop the quantum resistant security systems. Then the exciting part is the expansion of the quantum ecosystem. You can see that the startups are rapidly emerging and each focusing on different aspects, like from hardware innovations, quantum software to industry specific applications. So it's not only the private companies, even the governments are investing heavily in quantum R&D, aiming to secure strategic and technological edge in this emerging race of quantum. So in conclusion, I can say that the quantum computing is not just another step in evolution of technology. It is a giant step that redefining the very limits of what we can compute, solve, and secure. Like from drug discovery to global finance, from logistic optimization to traditional encryption. So quantum computing is reshaping the industries and solving the problems that were once considered to be impossible. And so already the quantum era has begun. And that's all from my end regarding the quantum computing. And as this session is about the National Technology, like a celebration of National Technology Day, again, I should remind that the technology is more than just circuits, code, or innovations. It is actually a force for a transformation to build a better tomorrow. So if you come across the leaders, thought of the thoughts of different leaders, and where they have put different messages during this National Technology Day. They have a common message that we have to embed sustainability, inclusivity, and human-centric design at the very core of every advancement what we pursue. That is actually this National Technology Day. Again, like it stands not only for celebration, it is also for a call to action. So technology must be driven not by what is possible, but what is purposeful. Because the true progress is not about the invention, but it is about the intention. So it's about using innovation to uplift, include, and empower. And the future belongs to those who build with purpose and those who are committed not only to creating, but also to educating, enabling, and elevating the every section of the society. So that's all from my end. And happy National Technology Day. And thank you. Let us move forward with the purpose for a brighter, inclusive, and empowered India, and accelerating ourselves towards the vision of Vikshit Bharat 2047. Thank you for patient listening. I've done for the day. So before I conclude, let me take this opportunity to thank the organizers for giving me the wonderful opportunity to share the insights on such a fascinating topic. And also at the same time, I would like to sincerely appreciate the organizer, Dr. Tangaraj, and his team for their dedicated efforts in successfully conducting this. I think today is the 79th webinar series. So your efforts in bringing together thought leaders, learners, and then like innovators are truly commendable. And such initiatives play a vital role in enriching the academic and the professional community. So wishing you a continued success in all your future endeavors. So thank you once again for making this platform possible and impactful. And I believe that this session would have sparked your curiosity. So thank you.
Yes, ma'am. Thanks a lot, ma'am, for your wonderful session and also for your wonderful words. Because only the motivation we are getting from the again persons like you, we are very much again motivated, and thank you for your support, ma'am. So to show our gratitude on behalf of our IAS Salem Local Center and the committee, I invite Engineer Armum sir to propose vote of thanks.
Well, sir, thank you then. Dear sirs, it's my pleasure to say a word of thanks to everyone who have made today's session a memorable one. First of all, I would like to thank the chairman and secretary of IEI Salem Local Center for their invaluable concern for organizing the seminar Engineers Talk series continuously for the 79th consecutive week. Thank you, Chairman sir and Secretary ma'am. And it's my bounden duty to thank Dr. G. Fatima, Professor and Head in Computer Science and Engineering Department at the Iman College of Engineering, for her presentation on the title, Quantum Computing, Redefining the Limits. Thank you, ma'am, for your wonderful presentation. Thank you very much. And I would like to thank the Engineering Talk team members, Dr. R. Satish Kumar, Dr. A. Kumaravelu, and Engineer K.S. Silvam sir, and the staff of IEI Salem Local Center, Engineer T. Tiagu, and our most valuable members of IEI Salem Local Center for their support in organizing this seminar in a wonderful way. Thank you, one and all. Thank you very much.
Thank you, sir. Thank you, madam.